The SIMTAP project was carried out between 2019 and 2023 as part of the PRIMA program. The partnership consists of 8 entities from Italy, France, Malta, Turkey and Germany. The project aims to develop a multi-trophic aquaponic system to produce marine fish along with edible crops. Aquaculture has grown faster than capture fisheries in the last decades and is expected to expand further in the next future. Aquaculture depends on fishery and agriculture, because fish meal and oil, soybean and cereals are the main ingredients of commercial fish feed. However, overfishing of forage fish and intensive agriculture have negative impacts on the environment. SIMTAP is an innovative technology to reduce the consumption of commercial feed and the use and contamination of water resources in inland aquafarms. The image shows the classic freshwater aquaponics scheme. Cooperating species, such as fish, bacteria, plants, require inputs, at least water and fish feed, and generate outputs, such as sludge and exhausted water. The integrated multitrophic aquaponics system partially replaces mechanical filtration with the presence of detritive and/or filter feeder organisms or DFFO. From this scheme comes the SIMTAP concept, in which fish feed is also based on components derived from DFF organisms that can be partially produced within the tank itself. In addition, any external source of microalgae can contribute to the feeding of DFFO, thus increasing their biomass and consequently reducing the need of commercial fish feed. In a circular economy perspective, nutrients and water discharged from hydroponic greenhouses can be exploited as a growth medium for microalgae. The SIMTAP project has its focus on the production of marine fish of high commercial value, such as sea bream and sea bass, and therefore enables the exploitation of saline or brackish water sources combined with the cultivation of halophytic plant species and/or marine seaweeds. This schema was applied to the construction of the SIMTAP prototypes in Italy, Turkey and Malta. The SIMTAP in France is slightly different. The SIMTAP system in France was set up in the oyster pond facilities of the Lyceum of Sea and Coast, in Bersafranc, on the Atlantic coast. 3 main ideas drove the design of this system. Firstly, we selected species of commercial interest and playing complementary roles in the ecosystem. Secondly, the natural biodiversity and the properties of the earthen pond were considered means to limit environmental impact. Lastly, fish are fed with plant-based feed complemented by mussels discarded from local shellfish producers. The system consists of 4 ponds hosting different species. At high tide, the water gets into the system from the gate and then is pumped to the ponds. The first pond hosts sea bream, release organic matter and nutrients, including nitrogen and phosphorus. The natural populations of crustaceans, invertebrates, phytoplankton and zooplankton benefit from these nutrients. The other ponds host oysters and clams, which benefit from the phytoplankton and organic matter contained in the water. The ponds also host curuma shrimps, which search for invertebrates at the bottom. Doing so, shrimps clean up the oysters and contribute to water aeration and the supply of mineral elements to phytoplankton. The different species performed well in terms of survival and growth. This fish farming system offers new perspectives for aquaculture in coastal ponds. Fish meal and fish oil are the main ingredients of aquaculture feed, or aquafeed, because they are excellent sources of polyunsaturated fatty acids and proteins with well-balanced amino acid profile. However, these ingredients derive from forage fish fisheries, and the huge growth of aquaculture has caused an overexploitation of marine natural resources. So, alternative feed ingredients are necessary for sustainable aquaculture. One of the goals of the SIMTAP project was to assess the effect on fish growth and fillet quality of the replacement of commercial aquafeed with an alternative diet, which consisted of detritivore and filter feeder organisms that could be produced in multi-trophic aquaculture. Different experiments were conducted in France, Italy and Turkey with 2 marine fish species, gilthead sea bream and European sea bass. These are the most valuable fish for multitrophic aquaponics in the Mediterranean countries, as found in a preliminary study performed using a multi-criteria decision analysis method, the DEXI open source software. In the experiments conducted at the University of Pisa, the alternative fish diet consisted of a mixture of mussels, clams and parakeet worms. The alternative diet also contained sodium chloride and other minerals. Sea bream and sea bass were reared in the SIMTAP system at water salinity of 25 or 10 grams per liter respectively, which is much lower than the salinity of seawater. Both fish species adapted well to the SIMTAP system. Fish were very greedy with the new diet and grew as fast as the fish fed the standard aquafeed, as shown by this graph where the individual weight of each group of sea bream is plotted over time. The marketable size of both fish groups, more than 300 grams, was reached in about 9 months. This performance was even better when compared with the standard growth curve of sea bream under the same temperature conditions. The fish fed on the alternative diet contained more essential fatty acids with a higher ratio between omega-3 and omega-6, compared to the fish fed with commercial feed. The fish fed with mussels, clams and worms were similar to wild-caught ones, notably for the content of omega-3 and the fillet texture. SIMTAP has been designed for the production of marine fish, such as sea bream and sea bass, in salty water. Therefore, only plants with high tolerance to salinity can be grown in this system. Most of the crop plants are glycophyte and do tolerate a high salt content in the soil or in the hydroponic solution. Halophyte plants, instead, can grow well at very high salinity, even in seawater. During the project, the focus was on 3 halophytic plant species: red orach, sea beet, and salicornia. Red orach and sea beet grow well with salinity level of 10 grams per liter. Salicornia tolerates even higher salinity, up to 30 or more grams per liter. Salicornia is the most interesting crop, even if its shoots are still a niche product, at least in Europe. The market price of salicornia is close to the price of farmed fish. Indeed, high salinity is necessary to harvest fleshy and succulent shoots of salicornia. The best salt concentration for this species grown hydroponically ranges between 10 and 20 grams per liter. Red orach, sea beet, and salicornia belong to the family of Amaranthaceae and can accumulate sodium and oxalate. Therefore, they should be consumed moderately or after boiling. The SIMTAP is a particular aquaponic system where crop plants and fish in marine or brackish water are grown with detritivores and filter feeder organisms, or DFFO, in the same water stream, while unicellular algae, or microalgae, are grown offstream. In the SIMTAP, microalgae are cultured for different purposes. They can remediate the exhausted nutrient solutions discharged from greenhouse hydroponics, in particular removing inorganic nitrogen and phosphorus. Moreover, microalgae are rich in polyunsaturated fatty acids, especially omega-3, and then are excellent ingredient for the diet of the detritivore and filter feeder organisms. Microalgae culture is also a source of non-saline water to compensate water loss due to crop transpiration and direct water evaporation from the aquaponic compartments. Therefore, freshwater microalgae species with some degree of salt tolerance are suitable for the SIMTAP. In the experiments carried out at the University of Pisa, a native chlorella-like algal strain was cultured in low-cost photobioreactors. This strain had been isolated from a pond where municipal landfill leachate flowed before wastewater treatment. The photobioreactors consisted of V-shaped tubular plastic bags, hanging from a metal frame and containing about 100 liters of growing medium, which was continuously aerated by a blower. The experiments were conducted in greenhouse in 3 different seasons to compare the productivity of chlorella alga grown in a modified standard growing medium, the TAP medium, or in the effluent from a greenhouse hydroponic cultivation of tomato. There was no significant difference between the 2 growing media as regards the daily production of dry biomass, which however was considerably influenced by the growing season. The biomass productivity markedly increased when columnar photobioreactors were employed for the microalgae culture, as it was observed in another experiment conducted in early autumn. Microalgal cultures showed to be more efficient in removing phosphorus than nitrogen from the greenhouse effluent. The removal efficiency was up to 96% for phosphorus, while it did not exceed 67% for nitrogen. To find the best location and landscape integration of a SIMTAP system, a land suitability assessment model has been developed at the University of Bologna. The model integrates geospatial technologies and multi-criteria decision analysis, and considers environmental conditions in relation to fish and crop needs, availability of resources such as water and infrastructures, potential access to labor and market, and potential interferences with other land uses and activities. Criteria and constraints have been identified through a participatory process, based on panel discussions, focus groups and surveys. After data collection and preliminary processing, all criteria have been spatialized and then reclassified to obtain a land suitability map for each criterion. Proximity to different types of water sources has been analyzed, as well as topography and temperature, to allow good crop and fish growth and reduce energy inputs for climate control. Proximity to infrastructures and facilities for the system functioning has been analyzed in a circular economy perspective, considering water, nutrients and thermal cascades from greenhouses and industrial activities. Potential access to consumers and contribution to occupation have been also considered. Finally, current land use has been analyzed to reduce conversion issues and minimize interferences. All the criteria have been assigned a weight based on their relative importance. Then, using a geoprocessing weighted overlay, all the criteria have been combined and merged together to obtain the final suitability map. From this map, areas with constraints have been excluded with a Boolean overlay. For example, in this map for Emilia-Romagna region in Italy, the constraints are represented in black, while the other scaled colors represent different levels of suitability. Green and blue show the best areas for implementing a SIMTAP system. The model has been tested in various areas in different Mediterranean countries. A geodatabase will allow, also after the end of the project, to support the implementation of SIMTAP systems in different local contexts, adapting the criteria and parameters of the model. The application of ICT and IoT in the agri-food sector proved to increase the efficient management and sustainability of agricultural and livestock systems, and ensure food safety and traceability. One goal of the SIMTAP project was to design and build an IoT-based integrated smart monitoring and control system, or ISMAX, of multitrophic aquaponic systems. The system allows the acquisition, storage, and management of large datasets of physical and environmental features. The ISMAX has a local part and a remote part. Sensors and nodes belong to the local part. Sensors are plugged to the nodes, which are wirelessly connected to the gateway, LoRa. The gateway is connected to the internet, sending data to the cloud and to a remote server. The nodes have been designed for handling both grid and photovoltaic energy supply. They can host all the most common interfaces to install different types of sensors. For instance, for air temperature, light intensity, and physico-chemical parameters of the recirculating water in the SIMTAP, such as pH, salinity, dissolved oxygen, etc. The ISMAX installed in the SIMTAP prototypes built in Italy, France, Turkey and Malta met all the system requirements, proving to be precise, flexible, and affordable. The environmental, social and economic sustainability of SIMTAP systems has been assessed through a multi-criteria evaluation model, the DEXIAQUA. The assessing criteria, attributes and indicators were selected by a panel of experts. Once quantified, each indicator has received a qualitative score through comparison with predetermined threshold values. Using different weights, the indicators has been aggregated to calculate the overall sustainability score, which ranges from very low to very high. 7 aquaculture systems have been analyzed, 3 commercial aqua farms in France, Italy and Turkey, taken as reference, and 4 SIMTAP systems, which were defined based on the experimental data collected during the project. For the Italian system, the study considered 2 different scenarios regarding the fish diet: commercial feed based on fish meal and fish oil, and an alternative feed consisting of mussels, clams and parakeets. The quality score ranges from medium-low to medium-high for the reference farms, and was medium-high or high for the 4 SIMTAP systems. Excellent economic results of the SIMTAP systems was due to the large production of salicornia as fresh vegetable, and parakeets as baits for sport fishing. In conclusion, SIMTAP systems have a better overall score than the commercial aqua farms. This is SIMTAP.